Hello students, welcome back. We just completed section 1 of this notebook, which corresponds to chapter 6 of our textbook. Now let's go to chapter 7, interval estimation, but we need some preparation, and that preparation actually comes from chapter 5. Let's discuss that before going over to chapter 7. Alright, let's begin with a reminder. The random variables x1 through xn are said to be independent and identically distributed if they are all independent from each other and they all follow the same probability distribution. For example, an odd model with replacement. A collection of independent and identically distributed random variables is called a simple random sample. And here are some properties of simple random samples. Expected value of sum is the same as the sum of the expected values, and they're all the same, so we have n times mu. Now from here, divide by n, then what do you get? Expected value of mean, or the sample mean, is mu. Next, variance of sum is the same as the sum of the variances, and they're all the same, so we have n times sigma squared. And then now, divide by n. Divide by n inside, so sum divided by n, so we have the mean, the sample mean. But you see, if I take 1 over n outside my variance, it becomes 1 over n squared, because you see the definition of the variance comes from square. x1 minus expected value squared, x2 minus expected value squared, x3 minus expected value squared, and so on. They add them all up and divide by, that's how you define the variance. They all came from squared. That's why we have this 1 over n squared. So from here, not just dividing by n, we divide by n inside, but outside we have to divide by n squared, and that's why we're having sigma squared over n. And one more. Therefore, the standard deviation of the sample mean is equal to square root of this over square root of n. And this quantity is often called the standard error. We're going to come back to that in, well, maybe in some of these examples we'll come back. Oh yeah, here, 2.7. For the proof, by the way, please look up chapter 5 of our textbook. The proofs require multivariable calculus, so please be warned. Alright, the next topic is sampling distribution. What is a sampling distribution? The distribution of values of sample statistics is called sampling distribution, and we can consider various statistics. By the way, if you have just one sample, then you just have sample statistics. You don't have distribution of those. Now, if you do not have the sample yet, then depending upon what kind of log you have for sample, you may have different possible values of sample statistics, you see, and how they are distributed. That's what sampling distribution is all about. Now, how do you visualize that? Probabilities. In order to visualize that, you need many different samples. You see, if you want the probability distribution of, say, coin tossing, you cannot get it by tossing just once. You have to toss many times to see the probability distribution of coin tossing. Same as rolling dice or picking some balls from an urn, things like those. So just taking one sample, you get sample statistics, but that's it. In order to see sampling distribution, that is the probability distribution before selecting a sample, you need to take a lot of samples and look at those distributions. So each sample is the actual repetition, You see, each sample is n independent repetition of the same thing, and you have, say, 500 samples. So we are talking about repetitions of repetitions. So things can be a bit confusing. I'll do my best lessen that confusion by appropriate visualization, but theory goes like this. The key thing is the probability distribution before taking the sample, but how do you visualize it? By taking one sample, you can't. By taking many different samples, you can see the sampling distribution. Well, let's go to some easier examples, maybe not important, but some easy examples so that you get a hang of sampling distribution first. And then we're going to go over to some more important examples, sampling distribution of sample means. Okay, let's begin with a trivial example. Excuse me, I take it back. It's not trivial. It's an interesting example, but not that important yet. Just try to get an idea, get a hang of sampling distribution. That's it. Roll a pair of dice 100 times and record its range. That is, higher number minus lower number. If you do it just once, then you get a single statistic, higher number minus lower number, but that doesn't tell you anything about distribution. You need some repetition, but 100 repetition, let's see, this is what you get. The difference between the highest and lowest number may be 0 or 1 or 2, 3 or 5. And this program is randomized, so I can run it again. So you can consider a simulated roll of another 100 rolls, another simulated 100 rolls. But you see, you get simulation, yes, but I still don't see a good idea of distribution. So let me increase the repetition. Roll 1,000 times, 10,000 times, 100,000 times. Now, if I run it again, not much change. Previously, run it again, a lot of change. So it's really hard to make any kind of prediction. So this kind of thing must be basically what you see as a sampling distribution of the range. Now let's consider a similar kind of situation. Choose a pair of integers between 0 and 20 and get the range. High number minus lower number. Previously, roll a pair of dice, so numbers were from 1 to 6. Now, from 0 to 20. Here's a histogram based upon 100 selections, 100 repetitions. Another 100 repetitions. Another. Any pattern? I don't see anything. Repeat 1,000 times. Better? Not much. 10,000 times. Now I see some pattern. You see, they're not really changing a lot. 100,000 times. Yeah, here we go. It's asymmetric. Going up and coming down like this, almost linearly. Those kind of things are examples of sampling distribution. I selected range, but there you go. Now, here are a little bit more complicated situation. Roll 4 dice this time, and then get the range. Based upon 100 rolls, another 100 rolls simulated. I can't really see anything. Let's go to about 100,000 rolls, and what do I see? Yeah, like this, going up and down, asymmetric again. Now choose 5 integers between 0 and 20 and get the range. Previously 4 dice roll, so 4 numbers from 1 to 6. But here 5 numbers from 0 to 20. Getting the range, okay. 100 repetitions. not much there. It's difficult to see the probability distribution. So let me increase it to, all right, 100,000 repetitions. And what do I see? Yeah, we have an asymmetric going up like this. Hit the mode and coming back down. And then it's not linear. Here we have concave up, concave down, and there must be an inflection point somewhere here. And do you see this thing may be converging into a certain probability density function as a limiting situation? It's likely to be. And what kind of density function do we end up getting? That could be an important problem, but range distribution is not something we are interested in for the moment, so let's just move on. Just try to get a hang of sampling distribution. That's it. So sampling distribution, you're looking for a probability distribution of sample statistics, and if you just get one sample and get sample statistics, you just get numbers. They don't give you any idea of probability distribution of each sample statistic. So how do you do that? By repeating it. So one sample is already a repetition, and then we have repetition of repetition going on. This example is rather trivial. Frequency distribution. So roll a die, and then what kind of frequency you get. Well, if I increase the repetition, I can clearly see what's going on. Hey, it's uniform. Yeah, each outcome is equally as likely. Duh. Roll a pair of dice a number of times and record the sum and the product. Here we have sum and we have product for 100 rolls. Hard to see anything there. Let's see. 10,000 rolls. Here I have definite pattern, triangular, unimodal, and almost linear like this. And I don't know what's here. Clearly this is multimodal. Let's see, 100 times. 100,000 times. Yeah, kind of triangular here, multimodal here. Those kind of things are examples of sampling distributions. So, do you get the hang of it? And we're looking for the probability distribution of each statistic of sample. And by getting one sample, you get nothing. So you need a lot of repetition. But even one sample is obtained by many repetitions, you see. Each random sample is actually x1 through xn, and n can be humongous. But repeated many times still, and that's how you get sampling distribution visualized. Now, among those sampling distribution, the most important is the sampling distribution of sample means, and looks like that's something I'd better start in the next video. So for now, let's be content with sampling distributions and some visualizations.